Okay, good afternoon, everybody, and welcome back. We're going to continue our discussions about guns and gunshots today, and about how evidence that gunshot leaves behind can be utilized by criminalists. And we spent some time talking about how bullets, for example, acquire markings from the guns from which they are fired, and how this is a very important method of tying a suspect bullet to a gun that might have been used. But there's other evidence which gunshots leave behind apart from the markings on the bullets. And this in particular applies to the fact that what we're looking at when we fire a gun is that there is an explosion that takes place in the bullet itself. And that explosion is the result of a complex set of chemical reactions. Now, in the old days, they used to fill a bullet with a simple mixture of gunpowder. It's a mixture of ground up carbon, charcoal, whatever, sulfur, and a nitrite of some sort. A very simple chemical mixture, not particularly explosive, but good enough to do plenty of damage if packed into a bullet. But nowadays, that is not the case unless people are collectors and buy special bullets which are filled with gunpowder, or black powder, as it's called. Modern bullets, commercially produced, usually contain a smokeless powder, is referred to. And a smokeless powder is a highly explosive compound of various different chemicals, which themselves are explosive. Now, I'm not expecting you to remember all of these chemicals. That's not the point of showing you this diagram. It's just that I want you to see how complex these mixtures actually are and how many different things are included. And remember that each of these chemicals that we see here may leave a trace. It may leave a trace afterwards of the explosion. And these mixtures are proprietary mixtures. They are particular to different manufacturers. So that in itself, contained in this list, is information. And that despite the fact that they're going to explode all of these, they may leave traces which can be interpreted in one way or another. So in this part of the bullet here, the bulk of the explosive mixture is composed of three highly explosive compounds. The two that you need to remember: nitrocellulose, it's also called gun cotton; nitroglycerin, which you've probably heard of, and one that you may not have heard of called nitroguanidine. It's these two that I want you to remember. These are all nitrogen-based compounds, and these organic nitrogen compounds tend to be very, very unstable and very, very explosive. They contain a tremendous amount of chemical energy. So these three together, yeah, they're very unstable, but in this powder mixture, there is a whole lot of chemicals are put in this list here, which are stabilizers. They reduce the fragility of these compounds. They make them much less sensitive. The explosive potential is retained, but they're not going. Nitroglycerin, for example, is highly reactive, and if you disturb it inadvertently, it can explode, but not in this form because it is stabilized here by these compounds. So there's also all of these different kinds of chemicals built into this. They sit packed in here. They're packed by mixing them with substances which are essentially inert, but which make them malleable and easily manufactured. And it's packed into the bullet casing here. That does not explode very easily. It has to be exploded by explosion of a primer. Now, you've heard about this before. We talked about primers about the structure of a bullet in our previous discussion. The primer is a small metal casing. This casing contains a highly explosive, very unstable set of compounds, which can be detonated by impact. So when a firing pin hits this little collection of high explosive here will explode, and that is sufficient to detonate this. It's sufficient to detonate the charge that is present in the bullet casing. But this primer here itself is complex. This is the usual main explosive compound, lead stiphanate. And that is very, very unstable, and it's mixed with things which actually destabilize it. So it's ready to go. It will explode when it is subjected to sudden friction. And then there are a whole lot of other things which add to the explosive nature of the primer. And these all, it's not very much of it, but these can all leave a signature. They can leave a signature in the explosion as it takes place. So when this explosion happens, most of this charge is going to be exploded, and a lot of it is going to be consumed entirely. And we'll have a lot of carbon produced just as soot. But then there's also a lot of material which is incompletely combusted. This explosion is by no means 100% efficient. And the explosion itself contains a signature of many of these chemicals in it. So we have a chance, if we could only get hold of a sample of the gases produced, we would have a chance of being able to analyze it and maybe be able to say what was the composition of this charge. And since the charge is proprietary, we might even be able to hazard a guess as to which manufacturers could have produced it. So when we look fortunately, when we look at a real gunshot, we realize that we can indeed sample the products of that explosion, because this is what the explosion looks like as the gun is fired. All of that scalding hot gas exploding in that small little bullet casing. There's a huge volume of gas compared to the volume of the bullet casing. And that is what erupts out of the front of the bullet casing and propels the bullet forward. That explosion is incredibly energetic. It is very, very violent explosion. It is contained by the strong metals of the bullet and the gun, but nonetheless, it is a very violent explosion. And it is sufficiently hot, for example, that it may even vaporize small amounts of the bullet, especially if the bullet is lead. If we look at the front of the gun, what we see, first of all, here's the bullet traveling ahead and carrying with it part of this cloud of material, probably the finer particles. Behind here, we see that there's a large cloud of material, and that is going to be a mixture. It's going to be a mixture of completely combusted carbon from the substances used to make the charge, and a mixture of the incomplete materials and also vapor. And that vapor may contain metals. There are various sources for the metals. If you have a look here, look at our main primer mixture, it's lead stiphanate. There are some which are lead free, but they also have other materials, zinc, titanium. And look here, there are other lead compounds in the primer. That is the main source of lead, but you may also have some lead from the bullet itself vaporized into this cloud. it's vapor because it's so hot. And as it cools, these, not only the lead, but all of these vaporized compounds will crystallize, and they may settle somewhere where they can be sampled. Now that's the first thing. The next thing is to realize these particles here are flying very fast through the air, but the air is impeding them. They are being impeded by friction. So they are slowing down, and they slow down quickly. They are not propelled very far in front of the gun. The bullet certainly is. It has sufficient energy to go for a very long distance. But these particles do not. And they are going to stop moving in the air before long. But if there is any surface which is in these spaces here, that surface may have material deposited on it. And there's various bits of information that we could gather from what is deposited onto a surface. The first is that we can perhaps see by the shape and the type of deposit how far away the weapon was from that surface when it was fired. That's the first thing. The other thing is that we may be able to discern something about the compounds that were exploded in the gun if these particles are carefully analyzed. So the particles and their deposition can convey information to us about the gun, the gunshot, where the gun was, etc. So a skilled examiner looking at a deposit from a gunshot may be able to begin to think about how far away the gun was from the surface that they're examining. Now, if the gun is very, very close to the surface, in fact, if it's just about pressed or is pressed to a surface, whether it's cloth or whether it's unfortunately skin, when the gun is discharged, that cloud of material that we saw emerging, that is constrained. And it is, a lot of that gas is driven in underneath the surface that the gun is pressed against, and that surface balloons up and ruptures. And it usually ruptures in a star shape like this, either a cross like this, or there may be more points to it. But there's this distinctive cross or star shape, and immediately around it here, there is a dense deposition of soot and material from the charge exploding inside the gun. So all of that material that we saw emerging from the gun muzzle now is concentrated here. Around it here, you can see a faint halo. And that is material which is in the form of vapor. These are mostly particles comprising this blackened area here. But this around here is vapor which escapes from the side of the gun and settles and crystallizes out onto the surface. Very often, these are metals, often lead from the primer, for example, would do this. So this is very close up. In the case of a skin wound, very often what we'll find is that underneath this, there is substantial deposition of material from the gun flash. So you will find underneath the skin here, a lot of gun material, of powder material and everything deposited in underneath the skin. It's been injected by the force of the blast. So this is typical of a very close, this is typical of a very close wound. In addition, quite often if a gun is pressed up against the skin, it may leave markings of the gun, of the muzzle itself. The gun muzzle, for example, heats up tremendously as the flash passes through it, and it may actually scald the shape of the gun muzzle into the skin if it's pressed hard against it. The same thing will apply the contact to a material. It's the same kind of principle. You've got a surface like fabric or the skin, which traps all the gases underneath it, and then it balloons up and explodes to release those gases. And it produces, here again, there's a star shape here. Here is a dense deposition of material from the flash, and surrounding it here, you can see the fainter markings where vapor has escaped out the side of the muzzle and deposited. So that tells us that was very, very, very close. But as we withdraw, we get further away, then the shape deposition actually changes. And as I said, if you have a suspect weapon, you can actually test fire a suspect weapon to try and work out, can we get a match between a deposition that we see, say on a wound, and a suspect weapon, and get an idea of how far away the perpetrator was standing, the shooter was standing when they fired. But even if we don't have a suspect weapon, an expert can hazard a guess as to how far away, at least to say they were close by, medium distance, intermediate, or far away. So up close, we've already seen, get that typical stellate. A little bit further away, you do not have that rupturing. A lot of the gas that proceeds with the bullet, for example, has expanded out, and it is the bullet entering that causes most of the damage. It's not gases associated with the bullet. But you may still, if you're close by but not pressing on a surface, you will still have a dense deposition of soot around the bullet marking, for example, and then maybe a halo of crystallized, vaporized material, often of metal. As you get even further away, that gets more and more dispersed. The soot and products, they no longer form this coherent dark area. Instead, they start to form a diffuse area like this. On skin, we see some particular markings that I'll show you in a while. Some of these here, when this is intermediate distance, we tend to have the larger particles that are moving very fast, and often those which are still burning, traveling very fast, and they are the ones that manage to make it the longer distance. So we get this kind of stippling around the bullet hole at sort of intermediate distance. As we get further away, it gets more and more diffuse until it disappears almost entirely, and all that we're left with is the bullet mark itself. So, especially if the criminalist has access to a suspect weapon, we can work out a rough distance away that a bullet was fired. But even if not, you can still hazard a guess. This is short distance. Again, you see what we see at a short distance. Here's the bullet hole, and then around it, a dense impression of the soot, and then a wider halo of particles and vapor deposited. Further away, it gets more and more diffuse until some distance away, it's only the large, fast-moving particles that make the distance and impact on the surface. So the first thing to notice here, when we look at this, one of the things to notice, I forgot to point out, is that lead, the vapor deposition, is the first to go. Okay, we only see that vapor deposition when the muzzle is really close by. We don't see it at any greater than by 18 inches away. We only have the soot and particles making an impact. So the bullet itself may have substances on the surface of the bullet which are wiped off as it passes through. This is passing through a test fabric, but the same thing might be noticed on skin. And it leaves this distinct dark marking, and very often rich in metals, because the bullet itself has been heated up, and the surface of the bullet may actually be wipe off to leave part of the mark, part of the wipe. It is called the wipe here. And at a distance greater than about 36 inches or so, the bullet wipe is probably practically all that you're going to see on a surface. You can still pick up faint markings, especially if this is treated chemically. So these are actual gunshots. This is a very close shot. And you can see here's the bullet hole itself. Now, a skin will actually char as well as the bullet enters. So it leaves a char mark often around a very close bullet wound. Around it here, you can see the dense deposition of soot there. And you're beginning, and you can see these large markings here from large particles. And if we were to test around here, we would probably find crystallized lead vapors, for example, around here that had escaped from the muzzle. Now, when you move even a small, short distance away to an intermediate kind of distance, say 12 inches or something like that, here's the bullet wound. There are a couple of things to be said about this. You'll see there's not much deposition around here. There's not much soot deposition, but you see all of this marking here. These are the larger, fast-moving, burning particles that have survived the distance, and they have impacted the skin and actually embedded into the skin. This is called tattooing, and it's an important feature. This is a feature of intermediate distance gunshot wounds. And there's another thing which is important about it, and that is the color. A pathologist looking at tattooing like this, if the tattooing is red or yellowish, orange, red color, then it's a sign that this tattooing was acquired as the person died. It's ante-mortem. It's acquired at the time of death. In other words, the flesh was still alive when it was tattooed. If gunshots have been impacted into somebody after they are dead, especially, for example, if a scene is staged or whatever, then the stippling has a different color. It's a bluish color. So there's information contained in the stippling. The stippling disappears as soon as the gun is even a smaller distance, shorter distance away. As we move away, the stippling soon stops. It may be difficult to analyze a gunshot mark, especially on cloth or things like that. And also, if it's passed through the hair, very often the hair will shadow the wound. It'll catch a lot of the particles so that the skin itself is not marked by anything but the bullet passage. So these have to be carefully examined. Here, for example, is a shirt, and this has you can see the bullet mark there. It might actually be quite difficult to see, might require some close examination to find it. But when it's viewed under infrared light, which is much longer wavelength than normal visible light, the bullet hole and the markings around it. The gunshot residue around it is clearly visible. A cloth like this can also be chemically tested, as we'll see in a while, which may also reveal gunshot pattern. And here's one here. That's all that you could see under normal circumstances. There's a bullet. This is probably wipe around the bullet hole itself, and some residue out here. But when this is chemically tested, chemically processed, you can see a distinct deposition here. And this deposition would suggest that this was fairly close, but not up against the surface. So it'd be sort of an intermediate distance. So that is that's the idea for stuff that goes out of the gun muzzle and ahead. But also important is the material which is spat out the side of the gun and backwards. The gun is not a sealed entity. Okay, it's not completely hermetically sealed. It's leaky to the explosion, and the explosion, don't forget, is violent. The explosion is very, very energetic, and it spews gases and the products of the explosion from many different openings in the gun. It will throw material out the sides of the breech, for example, and it will throw it backwards as well. And this means that this material here can be deposited on the hands and upon the clothing of the shooter. And this may be very significant because this can be tested for and examined for. And if it is found, it tells us maybe telling us some very important things. In addition, this material here will have a chemical composition which can be analyzed. And if somebody has material of that composition on their hands, and the same kind of composition is found at a wound or on a bullet or whatever, on the surface, at a crime scene, it is a strong indication that there is a link between those hands and that crime scene. So that may be a very significant finding. In order to test hands, very often there are simple ways of doing it. Samples are taken. That can be as simple as wiping with swabs or using sellotape in the absence of any other method. But there are special adhesive stubs which should be used. Here they are here. And these are labeled for particular areas so that you know that area has been stubbed with the adhesive stubs. And any particles can be picked up and can be analyzed in the laboratory. Here they are in use. And again, they are labeled, and there are specific areas of the hand which the examiner is trained to swab with this particular stub. As I say, you can do it with as simply as taking adhesive tape, but at least those adhesive stubs gives you a way of standardizing what you are doing. There is one technique which is very useful, and that is to use scanning electron microscopy. Now, scanning electron microscopy, unlike light microscopy, electron microscopy makes use of an electron beam instead of a light beam. And the advantage of that is an electron beam has a very small wavelength, and it means that we can get much higher resolution. We get much, much higher magnification than you can with a light microscope. But there's another advantage. In this technique of scanning electron microscopy, the electron beam is bounced off the sample. And that bouncing off the sample, we can actually make an image. and we get a three-dimensional image. Now this here is a scanning electron microscope of a surface on which vapor from a gunshot explosion has settled and crystallized out. And this, in fact, is these are metal globules. They were vapor, and once they settled on the surface and cooled, then they formed these globules. And so fine, you can easily identify, yeah, these are metal globules. They have a typical form of metal globules. But scanning electron microscopy has another huge advantage, and that is we're using an electron beam to bounce off. And when you do that, this creates X-rays of a particular frequency. They have a particular wavelength depending upon the substance that they are bouncing off. So what you can do is you can use your scanning electron microscopy not only to visualize, yes, metal and various other substances have been deposited on the surface and probably from a gunshot, but you can analyze these and see what they are. You can see what compounds they are, what elements they are, and that may give you a clue about the composition of the explosive charge and of the structure of the bullet itself. So that would be very useful. Okay, I also, in this, I do have a movie which I want you to watch. When I set these movies, please do watch them, but watch them in a particular way. Please don't just sit there like you would in the evening, just watching TV going past your eyes. Please sit with pen or paper and make notes as the movie proceeds. There is real information in these movies which I want you to acquire. Okay. So that you can watch at the end of this class. Okay, so all of this material that is deposited is referred to as gunshot residue. And all items from a crime scene where guns have been involved are liable to be examined for gunshot residue. A tremendous amount of information can be conveyed by where that gunshot residue is, on whose clothing gunshot residue is found, and what surfaces it is found on. Gunshot residue is not always easily visualized, and it might sometimes, especially clothes, garments, need to be treated chemically in order to visualize the gunshot residue. But there are many, many of these tests, and most of them produce a result like something like this. They actually come up as a different color, as a new color. Okay, so I'm going to leave it there for the moment because I want you to include that movie in our class for today. And I'll conclude this and our other section on tools and tool markings in our next class on Monday. Okay, and I'll see you then.